Okay, so we had said this stuff, right? So the right area is just going to be the sum of all of the areas of the right subintervals, all I of them, all n of them, right? As I goes from 1 to n, same thing for the left. And we came up with some pretty, like some pretty specific derivations of what the area of the ith right rectangle and ith left rectangle look like. Okay, and so where we left off, we were just in the process of sort of learning to do this, and we're going to apply this to an actual problem, right? So we said, we took the example of, should I turn that off or on? What you guys decide?
What?
Yeah.
Try it off.
You good this way?
We can just do a little test.
A, B.
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 Okay, B. I really did, that was close, I like that. Okay, so, so if we're gonna add up the right sum is the easier of the two, then, right? We just said that's gonna be the sum of the area of each rectangle, and all this amounts to is a height times a width, right? Of each rectangle. And we know that x sub I, that's, thanks to Marin, that's the a plus I delta x is our definition of x sub I. So we're going to start at the left edge, which is a, and we're going to take I steps of width delta x to get to the right edge of the ith subinterval. Delta x is just the area of the interval divided by the number of subintervals n, right? And so it all ends up, when we plug all that stuff in, we end up getting, this is really our final formula, right? Now what's really remarkable about this, look what we've done. We've written this right area in terms of what stuff? And look at the stuff in there. It's written in terms of constants, and specifically the value of the left edge of the interval, which is number we're going to know, right?
And the right edge.
And the right edge is B, the number of subintervals, which is going to be known, right? And then the function that defines, under which we're looking for area, right? So that's pretty good. So what if we were to apply that to something like, oh, let's make it something easy, like x squared. Okay? So what if we wanted to find the area under, so under f of x equals x squared, and let's just take the interval like we did before. Did we go from 1 to 3 or something? 1 to 4. Let's just go from 1 to 4 and let the number of subintervals be n. And then when we're all done, we can plug in different values for n and see what we get from those. Does that make sense? Okay, we can see, if we let n equal 3, what do we get? What if we let n equal 10, what do we get? Right? Does everybody understand that if I don't specify what n is, in my final answer, it's just going to look like an n, isn't it? Right? Everybody see that? Okay? And that's a parameter that we can then freely tweak. So what's A and what's B in this case? So A is 1, B is 4, n is n, and f of x is x squared. Okay? So then what does this end up looking like? The sum from 1 to n of everything that's inside the function is just being squared, right? So I'm going to have all of this stuff right here is just going to amount to some quantity squared. And the quantity squared is going to be 1 plus, what's the width of my interval?
3.
3.
Divided by n.
So 3 over n times I, right? So I can shorten that up a little bit. And then over here, I've just got 3 over n, right? Okay, so what about, and I guess we were in the middle of one other thing too. So what can I do? The index variable is I, right? That's the only variable that we're summing with respect to. Everything else, from the perspective of the summation, is a constant, right? And And we looked at an example right here, right? We'll jump right back to our problem in a second. We looked at this example where we had something like the sum of 6i from 1 to 17. And you guys right away told me that was 6 times 1 plus 6 times 2 plus yada, 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 6 times 17, right? If we rewrote that series, if we factored out a 6, look what we get. We end up getting, the sum of 6 times the sum of this thing, right? And what is that? As I goes from 1 to n, just 6, well, that's the sum of I, isn't it? Because I'm getting 1 plus 2 plus 3, so as I goes from 1 to n, does that make sense? So we're getting 6 times the sum, and really that 6 should be outside, shouldn't it? I've got 6 times this whole thing right here, which is the sum of I. So what's the point?
We could pull out 3n over n as a constant.
Yeah, right. So the point here is if I'm taking the sum of 6 times I, the 6 is a constant. It doesn't have an I in it, so that's a factor that can be pulled out front. It doesn't have to be a 6. It could have been an n, or it could have been an x, or it could have been anything. But because it doesn't have an I in it, it's a constant with respect to the summation, right? And so in our problem that we're working on now, notice that this factor right here, it's got an n in it, but it doesn't have an I, right? And so it's a constant. I can pull that out front. So we end up getting 3 over n times the sum of all this stuff. Okay, now what?
Squared.
Okay, I got to square that whole thing out, don't I? So the argument of the sigma, everything that's inside the sum, we can simplify that, right? So we could write that as 3 over n times the sum of, what do we get when we square all this out? Well, that's just a binomial, right? That's like a plus b squared. And so what's that square out to?
1 plus 6 over ni plus 9 over n squared.
Okay, good, good. And where are we getting that? That's good. So that's just our binomial expansion, right? A plus b squared is just a squared plus 2ab plus b squared, right? So this is like a and that's like b. So I get a squared plus 2 times 1 times 3 over ni, right? So 6 over ni plus b squared. What's that? What happens if I square that term? 9 over n squared I squared. Good. Okay. So now this goes back to probably last week, I guess. We can add those sums up because we know the summation formulas for the sum of a constant, the sum of I, and the sum of I squared, right? So let's page after. Okay, so then what's that going to give us? We break this into separate sums. We get this 3 over n out front that we'll just leave out there for now. We can always distribute it again later. And then we've got the sum of 1 from 1 to n plus the sum of 6 over n times I, right? What can I do with the 6 over n? if I'm gonna take this, pull it out front, so I get 6 over n times the sum of I, right? Plus 9 over n squared times the sum of I squared, right? I guess that's supposed to be one of those, right? Okay, and we know those, right? So what's that give us? What is the sum of 1 from 1 to n? N, yeah, so that's n plus 6 over n. What was the sum of I, do you remember? From 1 to n.
N times n plus 1 over 2.
Okay, good. And then plus 9 over n squared times, what was the sum of I squared?
2 something.
N times n plus 1 times
Plus 2.
2n plus 1 over 6, okay? And then remember that we've got this out in front, we've got this 3 over n that we could distribute through to all those, right? So what's that gonna give us? If we distribute this, if I distribute this to all the terms, the first one's just gonna be 3 over n times n, so I just get 3, right?
So what we're gonna be doing,
Question?
Are we figuring it, what are we figuring out right now?
Well,
It's just
okay.
the summation of the right side.
Yeah, and it's easy to lose track when you get really focused on the math, but what were we doing this whole time? We're just adding up the area under f of x equals x squared from 1 to 4, using right subintervals, right? So we're gonna base the heights of the rectangles on the right edge of each subinterval. Okay, see where we're going?
Yeah.
Okay, and we're just in the middle of doing a bunch of math, right? But what's exciting is what happens when we get the math done. You see some pretty cool stuff. So what happens if we distribute the 3 over n here?
There's an,
So I can simplify that, right? That's just 3 and 1. And then I multiply and I'm gonna get
which the ends will cancel out.
9, good, and I'm gonna get
One of the ends is gonna cancel out, right?
n plus, well, I could, you're right. Okay, so and on the bottom I'm gonna end up with an n squared, right? So I could cancel one of those. Okay?
The other cancel too.
And then over here we end up with, if I multiply by 3, we could do this, right? We could make that a 3 and that a 2. If I multiply by 3 over n, I'm going to get 9n times
All that stuff.
n plus 1 times 2n plus 1 over 2 n
one of-
cubed.
And then
Right?
cancel one of the ends. But don't the ends just cancel out?
So some n's are going to cancel out, so I could get rid of one of those, right?
Like if you.
Are
Are
we
we
gonna-
gonna, and then are we gonna?
We're gonna have to expand those out, right? So now, this guy just becomes a 3. What about here? This one, on this one, we're gonna get,
9n plus
if I split this up, split the fractions up, I'm gonna get 9 times n over n plus 1 over n, right? N plus 1 over n, same thing, everybody agree? Okay. Here, I'm gonna get 9/2 times, let's go ahead and expand out the top. What's that gonna be?
2n squared plus n plus 2n.
Well, plus, I'm gonna get, right, just 3n,
Plus 1.
plus 1, okay?
Over.
And then each of those is gonna be, I took the 2 out, each of those is gonna be divided by n squared, right?
Mhm.
Because I've got a common denominator of n squared, right? Okay, so now we just have to add up, we can simplify some of this stuff, can't we? So this one's gonna become, the n squareds cancel. Here I'm gonna cancel an n. There they cancel and become 1. So now let's just add up like terms. Okay, what do we get? So we get 3 plus, if I distribute, I'm gonna get 3 plus 9 plus 9 over n plus, if I distribute here, I'm gonna get 9 plus 27/2 over, or 27 over 2n, right?
Yes.
Oh, yeah.
Plus
9 over 2 and.
9 over 2n squared. Okay. And then we could say 3 plus 9 is 21. Plus, what about here? I've got 9 over n plus 27 over 2, and that's the same as 18 over 2n, right?
Mhm.
So that's going to give me 45 over 2n plus 9 over 2n squared. Okay, so that's my area. There's, we'll call that R sub n, right? Because that was the right area for n rectangles.
There's an n in there.
Yeah.
How do you like find a quantifiable area?
Okay, well, so it's gonna vary, and here's how it's gonna. Oh, we have like 1 minute. Is that right?
Yeah.
Oh man.
Well, that one fight really.
Wait a second, is it just gonna end up being like really close, say
Is
it's
there
gonna
a,
be
is there a
really close
shortcut
to
to this?
21?
Please tell me there's a shortcut to this.
Eventually, yeah.
Wait, Mr.
Why
Oya,
not now?
Mr. Oya, is the.
Because you guys don't know enough math to do the shortcut
area
yet.
just gonna end up being really close to 21?
Yeah.
Or is it 21?
It's the actual area is gonna be 21.
What?
Because as you approach infinity, it's gonna just end up being plus 0, plus 0.
So, okay, hold that thought. We'll pick this up tomorrow.